going on to measuring the impact, how do you go about doing that? Is it the number of researchers working in this field, or the number of funds raised, or are there several measures?
There's several measures, absolutely. And so on the research side of things, absolutely we measure our impact by the number of new researchers we're able to bring into the field. That's probably one of the biggest metrics of success. At our two research workshops, we basically had some of the brightest minds in cancer genetics and drug development come together and come up with a research roadmap for steps that we need to take to be able to ultimately reach the cure. And so another big metric of our success is accomplishing the milestones laid out in that research roadmap. And so that includes things like making tissue and cell lines available to Chordoma researchers. We've distributed the only valid Chordoma cell line to 27 different research labs, most of whom were not studying Chordoma in the past. It's been a big challenge with Chordoma. Many people have tried to create cell lines, and only one lab has succeeded. And so they created the only validated Chordoma cell line. It was actually a lab in Germany, and we've had this cell line here at Duke for the last 3 or 4 years. Interestingly, though, there were 7 cell lines reported in the literature, and we collected all of them here at Duke because we wanted to use them, obviously. And when we started studying them, we realized that they weren't behaving as we had expected. And when we dug a little bit further, it turns out that of those 7, only 2 of them were valid Chordomas. The others were either not human or not cancer, or if they were cancer, they were not Chordoma. So this poses an enormous challenge and kind of a big red flag in that a lot of data that's been generated on these cell lines is actually not valid for Chordoma. And this, it's shocking and somewhat infuriating, but it's not a problem that's unique to Chordoma at all. It's baffling to me that cell line contamination, cross-contamination and misidentification is absolutely rampant in cancer research, and it's something that people tend to kind of push under the rug and ignore. So that's fine if your goal is publishing papers, because it's really easy to publish a paper on a false cell line. No one's going to check. But if your goal is finding a cure, you really have to make sure that that cell line is what you think it is. Otherwise, your results are not going to be valid. You're not going to achieve your goal of ultimately finding a cure. So, to your point of metrics, our metric is number of validated cell lines. Are these tools that the researchers are using, are they actually going to help solve the problem? Are they available to researchers? So a cell line locked in someone's freezer somewhere doesn't do anyone any good. So right now, the Chordoma Foundation is able to distribute one valid Chordoma cell line. Our hope is to ultimately to create a panel of 10 cell lines. So in terms of metrics, we're at 1 of 10. We ultimately want to be able also to distribute Chordoma tumor samples, which are also another very important resource that researchers need to study the disease. And we hope in the next 2 years to be able to accumulate 200 tissue specimens. And then in addition to the tissue samples, we want to link the tissue samples to clinical data. And the reason why that's really important is if researchers find a particular trait or feature in a subset of those tissue samples, you want to be able to correlate that and see if it, let's say, correlates with response to particular therapy, progression of disease, prognosis, or so forth. And without tying the biospecimen, the tumor tissue itself, to the patient data, there's no way to make that link. So you may find something, you may have no idea what it means without actually being able to correlate it with the outcome in the clinic. So establishing the biobank, establishing the registry is this collection of clinical data.
Just to interrupt, the biobank, is that the linking the tissue to the clinical data?
Absolutely. So the biobank is actually the repository of tissue itself. And the word biobank gets thrown around pretty loosely. People basically, if you have blood in a freezer, they'll call that a biobank. The thing is, though, again, our hope is to try to create a gold standard, something that is really going to be useful for the highest impact research possible. And in order to really apply the latest technologies, the latest genomic approaches to understanding the cause of cancer, you have to have very, very high quality specimen. It has to be flash frozen, so as soon as it's removed from the patient, it's got to be frozen in liquid nitrogen. And ideally, it would have matched normal DNA from the same patient. So that collection of DNA and frozen tumor is the biobank, and then the registry is the set of clinical data from the patients whose tumors are in the biobank, and it's very important that they kind of fit hand in glove. And that's often not the case. Oftentimes biobanks and registries exist independently, and the link isn't made. So the value of each by themselves is important, but it's together they're greater than the sum of the parts, basically.
And what you're doing with this biobank, is that something that's very unique in the field right now? Are you pioneering this new way of linking all this information together? And
so I'd say a lot of people are working on this, and we've been trying to find best practices and other groups that are collecting fresh frozen tumor tissue with matched normal DNA and with patient data. And we've done an exhaustive search across the United States. We've actually looked at 42 different biobanks. And we haven't really found any that are doing kind of this, creating the Cadillac, so to speak. There are people who are collecting paraffin-embedded samples, which are not as high quality and not as useful as the frozen tumors. There are people who are doing a great job with the registry, but who aren't collecting frozen tumor specimen. And so I do think what we're doing is somewhat unique. I mean, this happens at academic centers pretty frequently. I mean, there are really fantastic biobanks all over the country. The problem is that they almost always are used primarily by that one institution. And in the case of Chordoma, no one institution really sees large numbers of cases, not enough to generate any meaningful data. And so we need to be able to aggregate the specimens from all over the country and all over the world for that matter. Exactly, scale up, right? So rather than getting 2 or 3 a year from Duke, we want to get 2 or 3 a year from Duke and 10 from Hopkins and 10 from MD Anderson, put them all together. And even if patients have their tumor removed at Kalamazoo, Michigan, we want to be able to get that tumor also, because that that reflects how patients are being treated. And so that sort of infrastructure to be able to collect tumor from all over the country, no matter where the surgery happens, is, I think, something that's unique, and I hope will be a model that can be replicated, either copied by other groups, or potentially in the future that we may be able to partner with other groups to include other types of cancer in the biobank.
Well, to expand to this national network that you're talking about, this really brings up the issue of accountability that you touched on some before. So I was wondering what kind of accountability practices you use, and how do you implement accountability in situations where you've doctors and researchers and just multiple actors?
So that's a really great question. So oftentimes biobanks don't have, as you say, the built-in accountability or reporting mechanisms that I think are really valuable. So tissue gets distributed, data gets generated, and that data never gets captured or integrated with other data that's generated on the same specimens. And so let me kind of break that down a little bit. So if one particular tumor is sent to 3 different labs, and each of those 3 different labs uses different technologies or different approaches to study it, they're all going to generate different types of data which may be complementary, and which, when put together, may lead to discoveries that no one individual lab could make on their own. Now, if the biobank doesn't require the data to come back so that it could be analyzed in the context of all the other data that's generated on the same specimen, you totally lose that ability to make these new conclusions. And so built into our biobanking protocol is that requirement that when data is generated on specimens, that it gets returned to the biobank so it can be aggregated with all the other data, and you get this continually growing data set around each sample. And then every time the sample is used, it becomes more and more valuable. And there is, I think, a need for researchers to protect their data and not immediately put it out there, although certainly from my perspective, I would love it if researchers would put the data out in public domain as soon as it was generated. But the reality is right now they have to publish, and so they need a grace period to be able to get their data published. We allow for that. Once the data is published, then it has to go into this repository that we will maintain and make available to other researchers.
Well, what do you think about sustainability for your foundation? If you reach all these amazing goals and you're closer to finding a cure, or you find the cure, what do you see next?
No, we have a heck of a lot of work cut out for us, and we are by no means anywhere near the end, and we still have a long way to go to find a cure.